Okay, here is our sixth note set in the Unit 4 on reverb. If you remember, in the last one we looked at the early reverb, and now we're looking at the late reverb. And we're going to be using comb filters and all-pass filters. So we studied those earlier in the course. And so now we're going to put those to use here for reverb. And I've got 5 things listed here for reading. You don't necessarily have to read them all. This note set is largely based upon this one. There's that William Gardner again. Remember, he was the guy who invented the convolution reverb that algorithm that we studied. And I've been basing a lot of my stuff on this chapter that he wrote in this edited book. And I've commented in the previous videos that book is maybe hard to find, and if you can find it, it might be expensive. You don't really need the whole book. That chapter 3, best way to get it would be to go to your library and ask them if they can either get the whole book for you on interlibrary loan, or sometimes interlibrary loan services can get you just a specific section of a book. So tell them that you want the chapter 3 of that book, and they might be able to provide it to you as a PDF, which is what I did. So in particular, we're looking at section 3.4 in that chapter 3. Now, there's some other things here. The 2 textbooks that I kind of have as the standard books for the course, even though there isn't really a standard book. There is some stuff in each of those books on this, but it's nowhere near as comprehensive as what's in this chapter written by William Gardner. But then at the bottom, I list the 2 original source papers for this material. And this guy Schroeder, we've alluded to him before, is kind of viewed as the grandfather or the godfather of artificial reverb, digital artificial reverb. And these 2 papers were done quite a long time ago, 1961 and 1962. And they're pretty easy to read, although it's clear that this was in the early days of the development of digital signal processing, because he really does it in terms of continuous time ideas. So a lot of the terminology might be a little weird. And in fact, one weird thing is that he doesn't use hertz. He uses cycles per second, or CPS. And so the unit hertz, I think, was standardized and adopted maybe right before these papers came out. So it wasn't completely in standard usage now. But now everybody just says hertz. But back then it was cycles per second. So I thought I should point that out. They're pretty easy to read. So, and my guess is that even though the Journal of Audio Engineering Society is often hard to find their papers available openly on the internet, my guess is these 2 might be available. But again, interlibrary loan should be able to get those for you. That's how I got them. So let's dive into this. We've already been talking about Schroeder's insights, or we talked about some of these characteristics, rather. So we've talked about characteristics of reverb, and this was what Schroeder looked to for his insight. So this is coming out of Gardner's paper. He discusses this result, which we saw in the previous note set, or 2 back actually, where we said that the density in the frequency domain, along the frequency axis, the density of the modes increases quadratically as frequency goes up. And so here's a quote right out of Schroeder's paper. So this is his 1961 paper. He said, quote, "Many simultaneously excited and interfering modes result in a very irregular amplitude frequency response." So he's just pointing out that if you look at the frequency response, it's very irregular, but it's kind of on average flat. So even though you have all these ups and downs, And they're very closely spaced. So that's the other thing that he comments on. This isn't coming out of this formula, but it's coming out of what people perceive for good room reverbs. So from actual real room reverbs, people don't perceive all these ups and downs in the frequency response. They just hear it as a nice flat thing. So it's not coloring the sound at all. And so this dichotomy, this idea that there's all these irregular modes, all these closely spaced irregular fluctuations, together with the fact that we don't really hear them, is what has made it hard for people to simulate a real room reverb and make it sound realistic. So Schroeder says he's going to set out to just make a perfectly flat frequency response. Initially, he's just going to ignore the fact that there's all these interfering modes and all these irregularities, and he's just going to say, look, if people hear them as flat, I'm just going to make this be flat. So that's what he set out to do. He also gained insight from this formula, which we saw in the last two note sets ago. The echo density grows as the square of time, so it grows quadratically with time. So the number or the density of the echoes goes up and up very quickly as time goes on, or in other words, the echoes get very closely spaced, closer and closer spaced as time goes on. The way he describes this, again, this is a direct quote out of Schroeder's 1961 paper, gradually the echo density increases to a statistical clutter. I like that phrase. It makes me smile. And then he goes on and says that, after that first 100 milliseconds or so, that's the early response that we talked about in the last note set. After that, you can't really hear individual echoes. You just get this statistical clutter of echoes. And so when we're in large so-called diffuse rooms, the other thing that is noticed is that the modes that are there all have about the same reverberation time. Now, we saw a plot showing that the reverberation time of the Boston Concert Hall, Boston Symphony Hall, its reverb times did vary a little bit with frequency, but not a lot. So that's what he's saying here. So we want to try to strive for that. And another thing he's cautioning against is a lot of the early attempts to make reverb made the sound have a characteristic that would be like being in a room between two parallel walls and no wall here and no wall here. And so the sound just bounces back and forth between those walls. And that creates a periodic sequence of echoes. And so those periodic walls or echoes just sounds really bad. It has a fluttering sound to it. And so that's not desired. That's not what we would have in a good concert hall. So Schroeder decides, okay, I'm going to build a dense, non-fluttering time response. So those are the two things that he's decided. He's going to make this thing perfectly flat and in the frequency domain, and he's going to try to get it to be extremely dense and hopefully get denser as time goes on, but there should be no periodicity to the impulse response. So he lays out these conditions, and again, I'm pretty much I'm not quoting these exactly, but I summarized his 6 conditions. So he wants the frequency response flat. He gives a little caveat here as to what he really means or why he's saying that from a real room's point of view. But initially, he's just saying, I'm going to make my frequency response perfectly flat. That's his aim. He then says, despite the fact that it's flat, I need to have some concept of these modes of the reverberator. And I'd like these modes to overlap somehow, and I want them to cover the entire audio frequency range. And then he says, I want the individual modes to decay with equal rates. So we know that real rooms might have nearly equal rates. He's just going to go with perfectly equal rates. And then he's trying to get a very high density of echoes. So a little while after the initial impulse is sent into the room, he'd like to have a density of at least 1,000 echoes per second. Now, really, we'd like that to continue to grow, and it should grow quadratically. And we'll talk about that some more as we go on. And no flutter echoes. So we don't want it to sound like we're standing between two parallel walls. So no periodicities in the impulse response. And also he points out, we haven't really talked about this yet, but he points out that we also don't want periodic peaks in the frequency response, so along the f-axis. So that would be like a comb filter. And the reason that we don't want that is people had tried those earlier, and they do give a reverb-like sound, but they sound very metallic or hollow. It sounds like you're in a pipe. You take the long hose of a wet dry vac and just bang it on the floor, and you'll hear a metallic or hollow sound. So these are his 6 conditions that he's going to strive to try to make, and he'll take several stabs at this before he gets it right. So these papers are interesting in that he just lays it all out. I tried this, it didn't work. I tried this, it didn't work. Modern papers tend not to do that. They edit all that stuff out and just tell you, hey, I was so clever, I came up with this. But in reality, even modern day papers, there's a lot of trial and error until you get it right. But these days we tend not to say that. I like seeing a paper that says, well, I did this and it fell short. Then I did this, because it shows that that process of figuring things out. Okay, so let's look at the first thing that he does. So I'm showing that all 5 of these references cover this to some degree, but really I'm looking at Gardner's paper and Schroeder's very first 1961 paper for this coverage. And I'm using a lot of the figures and flow of ideas from Gardner's chapter 3 in that book. So an quote-unquote obvious choice for a reverberator. It is pretty obvious because we think of the comb filter as having this feedback that just keeps echoing something back, and that's kind of exactly what we're thinking of having for reverb, but it turns out that it's not very good because it fails almost all of the conditions that Schroeder put out. But fortunately, Schroeder started off with this and then realized, well, let me put this aside and try something else. And that didn't work either. We'll look at that in just a second too. Looked at an all-pass filter by itself, but then realized that, well, we can combine these all together. So ultimately, Schroeder's final idea is to combine the 2 things that failed, comb filters with all-pass filters. So 2 things on their own failed, but he realized by having explored those things, if I put these together, everything works well. Okay. So Schroeder started off just looking at this classic comb filter, and this is the transfer function. Now, like I said, If you go look at Schroeder's paper, you won't see Z's. You'll see things that are being couched more in a continuous time version that is mimicking what a discrete time system would do. So 1961, this was very early in digital signal processing theory being developed. So concepts of Z transforms were, I think they were available then, but were not widely used, except among those who were the innovators of DSP. So there weren't a lot of DSP practitioners at the time. So anyway, if you read Schroeder's actual paper, you won't see it like this. I think Gardner puts it in terms of true Z transforms. Anyway, here is the Z transform transfer function for the comb filter that Schroeder was looking at. And we know that we can transform that over into the time domain to get the impulse response. And we see that we get a sequence of delta functions that are spaced by M. There we see periodic nature. I mean, not truly periodic, but the spacing between every pair of echoes is M. And we see this G and G squared and G cubed. So if obviously G is less than 1, at least in magnitude, those will decay, just like we would want. So here's a picture of that. And this picture here is from Gardner's paper, and I've just added an additional axis in actual time. So this is in samples. So capital T is our spacing between samples, so that's 1 over Fs. So this is just showing you the actual spacing in seconds. So what is our echo density? Well, we're getting 1 pulse every m seconds, or mt seconds. So our echo density is 1 over mt pulses per second. And so remember, we want the echo density to be high, and since that echo density is reciprocally related to m, we need a small m value that will make these things closer together. So that's what we want. Okay, set that aside. Now let's continue to analyze this. So here's our transfer function that we started with. We can rewrite that as a difference equation. So we're just going around that. If you go back to the review material for this course, I had a little set of blocks. I think it was called system relationships for discrete time systems or something like that. Showed all the interconnections between difference equation, transfer function, frequency response, impulse response, block diagram, pole zero diagram, all of it. So we're just basically using that as a guide to look at all the different characteristics of this particular system. So we go from transfer function to difference equation. And then from difference equation to block diagram. So here's a block diagram. We've got an M sample delay. So remember, that would really be built by z to the minus 1 cascaded M times. We're just showing it as a single block there. And then we have a feedback through G, and those get added. So that's how we get that. But we can see what's happening here, right? Delta function goes in, comes out of here M samples later and goes back in. Well, now at that point, nothing else is coming in because the delta function has now gone to 0. So what comes out comes back in and goes through again, but it got hit by a G. And then now that thing that has a spike of height G now is G squared. And so now we can see that we would get an impulse response that looks like this. So everything checks out. That's good. It's good when we do that little sanity check. Now we can also just start with this block diagram. And from that, we can get the transfer function. So we can just write that Zm y of z. So if this is y of z, over here is z to the m times y of z. And that's nothing more than, well, v of z as we have it notated there. But it's x of z plus g times y of z. And from there, we can just solve for, put y of z on one side, swing the z to the m over to the other side, and we could now manipulate that to get the transfer function. Or we can, from this directly, deduce what the difference equation is. So again, we're just going around that diagram that I showed you back in the review section of the course. What else did we show in that review section? Well, once we have the transfer function, we can convert it into its z form. So here's its transfer function in z inverse form. Multiply top and bottom by z to the m, and those cancel, and pass that through the denominator, and we get this. And so now we see no zeros. Well, all right, no explicit zeros that are found by setting the numerator of the z form of the transfer function to 0. But remember, there are some implicit zeros, right? Any value of z that has an infinite magnitude plugged in here is going to make the denominator go to infinity, which will make the transfer function go to 0. So we say there is a 0 at z going to infinity. Any value of z. Remember, z is complex. So as we go to any value of z infinitely far from the origin, we get that the transfer function goes to 0. So that's where the 0 is. But no explicit zeros. So we have only explicit poles to worry about. And so that we set that z to the m minus g equal to 0, and swing the g over to the other side. So they're the mth roots of g. And so what does that mean? Well, I fudged a little bit here in my notes. I hemmed and hawed about how I should notate this, but I just said that the radius is g to the 1/mth, implying that that ends up being a real number. So in reality, the mth roots of g are that one real number plus a whole bunch of complex numbers, and all those complex numbers are all equally spaced by 2 pi m. So whatever this number is here, it's a positive number. Let's just call it m sub g. And so the poles are all going to be at positions that are m sub g e to the j k 2 pi over m. Remember, m is fixed. It's a parameter set there. So, and this k is just making us go around the unit circle, or around the circle spaced by 2 pi over m. So it ends up looking like this. This distance here, here's that number right there. That's the real root, the real mth root of g. And then we have that same distance. So these are all on a circle whose radius is equal to that real value there. And the spacing is this 2 pi over m. So the spacing and angle. So you should be able to deduce from this what value of little m that figure was drawn for. So these are the normal modes of this reverberator. So remember, we talked about those modes as being the resonances of the room, so to speak. And so, they'll be more pronounced as they're closer to the unit circle and less pronounced as they're farther from the unit circle. But we'll see how to set this radius for to achieve specific reverb goals in just a little bit. But since these are the modes, we need these modes to be very closely spaced. Now, this is an artificially small value of m, because what we see is to make these things very closely spaced, we need a large m value. Then we would get those very closely spaced modes that Schroeder is saying they need to overlap and cover the entire frequency range. Now, unfortunately, that conflicts with what we just saw for the time domain echo requirement. There we needed a small m value to make sure that the density or spacing of time echoes is appropriate. So we need very closely spaced time echoes. So we can only get one or the other with this approach. That's the downfall to this approach. And we'll see that thread going through the rest of the notes or slides here. All right, let's continue on. Let's convert this into the frequency response. So we go back to the Z inverse form, replace Z inverse by e to the minus j omega, and we get this. And then we can find its magnitude. And technically, I'm writing this out as magnitude squared, but I could get rid of the square there and put a square root over there if that makes you feel better to see that. And we see that the denominator is something that's going to be oscillating up and down around some point. And so the value of m, remember we're viewing this as a function of omega, the value of m is going to set the period of that cosine. So we'll get something that looks like this. And we can see, as we look at the extreme values that this can take, we can see what values this function will take. So its maximum value is at 1 over 1 minus g, and its minimum value is 1 over 1 plus g. Now, just a caveat, this figure assumes that g is non-negative and also not equal to 1, right? So strictly between 0 and 1, non-inclusive. G equal to 0 would make no sense, would it? And so if we look at the ratio of these things, we can find that that's 1 plus g over 1 minus g. So you can see what happens as we change g on that. And we can also figure out the peak spacing, right? The peak spacing is set by the periodicity of that, again, as a function of omega. So m is kind of like a frequency along the frequency axis. So that gives us a peak spacing of 2 pi over m radians per sample. So that's the peak spacing on this omega axis. But if we were to do it on an equivalent f axis, that spacing is now 1 over mt hertz. And I'm pointing out that, well, mt is the delay in seconds. So the peak spacing and the delay or the echo spacing are reciprocals of each other in this. And that's the problem, right? So we want both the peak spacing and the echo spacing to be small, but they are reciprocals of each other. So making one small makes the other one big. Another thing we can look at is how wide are these peaks. So wherever the height is, we say, well, I want to go 3 dB below that, and then how wide is that? So that would be the 3 dB peak width. And I didn't go through the analysis of that, but one could analyze that and you'd end up getting this result, the negative of the natural log of g. Again, we're assuming g is non-negative, and it doesn't have to be, but would be less than 1. So we see that that also has a dependence on m reciprocally. So if we pick a typical g value, and this is just gained by experience with real rooms, 0.7 G is going to give us a 3 dB echo loss. So every time something bounces off a wall, it loses 3 dB of power. Well, if we do that, this ratio is 5.7. So that's 15 dB. So that's pretty high. But even more important, if we look at this value, we plug in the values for that, we get that it's 0.11 times 1 over mt. So remember, 1 over mt is the spacing. So the width is just 1/9 the spacing. So these are going to be very evident ups and downs, and you would be able to hear those for the kinds of m's we would need to achieve the echo density. So that's the problem. That's the problem. So let's also try to get an idea for the reverb time of this filter. Just continue our understanding of this, even though by this point we are convinced this is not going anywhere, but it doesn't hurt to just fully ring out an idea just so that we can get some insight to it. It might come in useful later. So if we say, okay, it takes P echoes to drop 60 dB from its start. That's our definition of the 60 dB reverb time, T sub R or T sub 60 that we talked about before. So that means at the pth echo, its height will be G to the P. Remember, it started off with a height of 1 and then G squared and so forth. So on the P echo, it'll be a height of G to the P. But we want to look at this in dB. So take 20 log 10. These are not powers. These are levels. These are like volume levels or voltage levels. So set that equal to minus 60, the level that we want. And remember, we started off at G to the 0, which is 1, so that would be 0 dB. That's why we just put in minus 60. What we really want to know is when does it drop by to drop 60 dB or to drop by 60 dB. But in this case, it starts at 0 dB. Now we just solve for P to find out how many echoes we need. So the number of echoes is going to depend inversely on 20 log 10 of the G that we set. So now suppose we say, okay, I've got a delay value of M and a sample spacing of T. I can then say that the reverb time is going to be this value of P times the spacing between echoes, M times T. And now I'm just going to solve for M. So M, the value of M that I need to put in to get this reverb time is, I put in my reverb time, I put in this value of P in there, and so if I plug in something typical, like we said, 0.7 is something that most reverb people who study reverb would say is a reasonable value, and a 1 second reverb time. That's not a terribly long reverb. That gives us M on the order of 2,277. So now if we take that value of M and go back and plot our frequency response, and I'm zooming in, but still this is in kilohertz, so I'm going from about 2 kilohertz up to 2.5. So we're looking over 500 hertz here. We've got a bunch of spikes, but the peak spacing, if we plug all these numbers in to the values or the formulas we had on the previous page, these peaks are spaced 19.4 hertz apart. It's not at all the kind of spacing we saw a couple note sets ago where we were talking about less than a hertz spacing. The peak width was 2.1, very small compared to the peak spacing, and we can see that. These are very narrow peaks compared to the spacing. So we might be able to hear these differences or this fluctuation. So it certainly wouldn't sound flat. And remember the echo spacing was a reciprocal of the frequency peak spacing. So that would mean the echo density is the same number. So hertz versus pulses per second. So the echo spacing would be seconds per pulse. So that would be the reciprocal of that. This is not good. This is not going to give us a good reverb at all. It'll sound horrible. It will just sound like an echo, okay, not a reverb. And in fact, if we go back and look at Schroeder's 6 conditions, the only one it meets is 3. The reverb times of the individual modes must be nearly equal. And that just comes because all the poles are at the same radius. So We know that poles, when they go into the time domain, will lead to the pole value raised to the n and then a u of n kind of thing. So if they're all have the same radius, the magnitude of that they'll all go down the same. They'll all go down at the same rate. So it meets 3, but it doesn't meet any of the others. Certainly not flat. We just saw that. The modes do not overlap. Very narrow peaks spaced quite widely apart. We saw that the echo density was not very good at all. We had flutters, right? All the echoes are spaced by exactly the same amount, and we saw that there were periodically repeated peaks in the frequency domain. So everything is bad except for 3, and 3 really is the easiest one to get. So Schroeder then said, let me take a look at the all pass. And I don't think he actually said that. I think he was just screwing around trying different things. I'll show you where his language seems to indicate that. But anyway, it led him to an all pass reverberator. Again, I don't know if he was really aware of the concept of an all-pass filter. That concept was around, but I don't think it was necessarily widely known at that point about all-pass filters. Anyway, he discovered that this was a little bit better. It solved some of the problems, as we'll see, but still didn't solve them all, so still not good, but we'll see it makes a good building block. So there's 2 ways to see this motivation. One is the way Schroeder got to it, and then another is a more modern way for someone who's knowledgeable about all pass filters. So Schroeder said this. This is, I'm paraphrasing. This is a direct quote out of the paper, but then the rest of it is just a paraphrase of that. But we discovered that mixing the original signal with the comb filter output in the correct ratio gives a flat frequency response, which is an all-pass filter. Now, I think he does literally say that, but here's my guess. He was just playing around with this, trying to figure this out. And we already know that he was thinking about mixing the room reverberation with a direct form, a direct signal. So that's what he's doing here, mixing the original signal with the comb filter output. And I think he just kind of figured out that if they did that in just the right way, he got a perfectly flat frequency response, and then may have discovered that people were exploring all pass filters as just a generic building block for other things. So that's what I think. I mean, obviously I wasn't there, but based upon that terminology, I'm thinking that's what happened. But the other motivation for us, since we know about all pass filters, is to say, hey, if we want a flat frequency response, an all pass filter is going to give us that. And what we're going to do is pick an all pass filter so that the denominator will be the same as the comb filter's denominator. That way it'll have the same locations of the normal modes, but we'll still have a nice flat frequency response. So let's look at the way Schroeder got there. This was what he ended up with. And again, this figure's from Gardner's chapter 3, not Schroeder's paper. Schroeder, again, showed these in kind of a continuous time version of a discrete time system, if that makes sense. But this is basically what he was looking at in a more modern discrete time view. So the part that I have in the red box here is the comb filter that we just looked at. And what we're doing is taking the output of that and adding it to the input with an appropriate pair of weights and then adding them up. So that's what he got by saying mixing the original in the correct ratio. And it turns out that this gives a perfectly flat frequency response. So we just write out from the block diagram. If we go back here and we say, y of z, this is going to be x of z, and we'll call this h sub comb of z, we can see that we get something that looks like this. There's the 1 minus g squared that's weighting the output of the comb filter. Okay, I had a comb here, and on the previous slide I just wrote h sub c, but you get the idea. So that's writing that out, and so this is the new full transfer function of this new envisioned filter. So now we're just going to manipulate that. So I just wrote it out and I've plugged in for the comb filter that we've already analyzed. Now just a little bit of algebra. We can find a common denominator between these terms and then combine all those over that one common denominator. A bunch of stuff cancels and we end up getting that. And so we look at that, and now we know, in our modern view, we know how to characterize all pass filters, and we said, oh, it's going to have this kind of crisscross thing. So I don't quite have this in the right form, but if I that we looked at before, if I put this first, we'd see that crisscross of the relationship. But I've got these in the reverse order, so we see that we have a minus g and we have a 1. So that's the way that we talked about that before. So clearly this is an all-pass filter. And it has the same denominator that the comb filter had before. So we could just jump to this and say, I want to keep the modes the same. I want to keep the poles the same, but I want to make the frequency response flat. Okay, there's my new numerator. We can just jump right there. And so we know this is all pass, so its frequency response magnitude is going to be equal to 1. And so now we have a standard transfer function from which we can just write out our straightforward block diagram form. So direct form 2, if you're familiar with that phrase, or we could just derive what it looks like by writing out the difference, the resulting difference equation from this in the z domain, or just writing y of z, or x of z times this gives y of z, and then plugging this in explicitly. So we can write that out, and then we can see that we get a block diagram that looks like that. So that's our more standard block diagram form. Looks different than what Schroeder used. And this is just a little, perhaps a little easier to visualize and think about. So, but from Schroeder's view of his block diagram, the way he came up with it, we can actually easily see what the impulse response of this new reverb filter looks like, because we already know what the impulse response of this looks like. So if I put a delta function in here, it's going to go through here straight, get hit by the minus g. So there will be a spike down to minus g. We're assuming g is positive here, right off the bat. And then that goes away, and then there's a delay through here before we get anything contributing there. And that also gets hit by the 1 minus g squared. So putting what we know to get already together, here's the 1 spike coming from there, and then here's our old comb filter, but with a 1 minus g squared times it. So we did have a 1 before, now we have that. We had a g before, now we have that. So all the stuff we had before is just multiplied by 1 minus g squared. So that makes sense. What's our echo density? Same as before. We've not changed anything. So it's still 1 over mt pulses per second. So we still need a small m value, and that means that our modes are going to be widely spaced. So that conflicts with the requirement for dense modes. So we haven't fixed a thing here, except we have a nice flat frequency response. That's all we've got. So here's our all pass view of this, and I've just converted this from Z inverse form to Z form. I just want to see what the poles and zeros look like, just to get a full assessment of this kind of filter. So the poles, I'm going to set that equal to 0, and so the poles are just the mth roots of G. I'm going to set that equal to 0, And so now we get that the zeros are just the nth roots of 1 over g. So that means that the radius for the poles will be, again, here I've kind of skirted the issue, but this is the positive real number that corresponds to the nth root of g, where we're assuming that g is a positive number, strictly greater than 0 and strictly less than 1. And just like before, all the other poles will be spaced, they'll be complex valued, spaced around the z-plane with an angular spacing of 2 pi over m. And then the zeros are the reciprocals of those. So they're at a radius that's the reciprocal of this. But the angles are the same. And we saw that. We already knew that all pass filters have that relationship. So there's a nice picture. Again, m is artificially small here from what we would need. But you can see that at every angle we've got a pole and a zero, and the distances from the origin are reciprocals of each other. So that's kind of what we expect from an all-pass filter. So let's see, where are we now? So, well, we've picked up 2 more conditions. So we did have 3, and we retained that because we kept all of our poles at the same distance from the origin. But we've got a perfectly flat response because it's an all-pass filter. And there's no frequency response periodicity because it's an all-pass filter. So just by going to all-pass, it doesn't even have to be one that characterizes a reverb. We've got these 3. But really, none of these if you can't really say that those 3 alone really give you something that sounds like a reverb. They don't. So I'm just writing out what I just said. 1 and 6 we just get because any all pass will satisfy each of those. And condition 3, we already had those before. But notice that our modes are not visible in the frequency response magnitude. But we know that there are poles there. We're just not seeing evidence of them in the frequency response magnitude. That's okay. That doesn't mean they're not modes. That happens sometimes and happens in every all-pass filter. Every all-pass filter has a bunch of poles, but we don't see any evidence of their pole locations in the frequency response magnitude. So condition number 2 says that the normal modes of the reverberator must overlap and cover the full audio frequency range. So it's a little confusing here how to characterize that. What does it mean they must overlap and cover this range? So it's not met. Even though our frequency response is perfectly flat, we're still looking at the pole locations. And there's an alternate way to think about that. They're not seen in the magnitude, but they can be seen in the phase. And in fact, a better way to look at this is something related to the phase. We talked about this before, the group delay characteristics. So if this is our transfer function, we can write out the all-pass frequency response, and I wrote it out this way, and then I just factored this thing out in front. And now we can find the frequency response of that, or I'm sorry, the phase response of that. So this is going to give us this thing, and then we just apply our usual analysis, doing arctan on the numerator, arctan on the denominator, and then we can combine those 2 things together into 2 times an inverse tangent. Now, I do want to point out that Schroeder's formula for this is a little bit different. He doesn't have a negative sign here. That's because he's not talking about phase. He's talking about something that he calls the phase lag. So the word lag combined with phase already has the negative built into it. That's the lag part. So he doesn't need the negative sign for that. Now we find the group delay. So with phase, not phase lag, we have to take the derivative and then put a negative out in front. And so when we do that, we get something that looks like that. A constant in the numerator and something in the denominator that looks just like the denominator of the magnitude of the comb filter that we looked at. So that's what I'm saying here. And now we can see that by looking at the group delay, we see that there is this kind of unequal treatment across frequency. And this is a direct quote from Schroeder's paper. This is his argument for why this doesn't meet condition number 2. And this is a plot of that group delay. And you can see it's got the same kind of nature of, very sharp, widely spaced peaks in group delay that we saw in magnitude for the comb filter. Okay. Condition 4 and 5 are not met. So echo density is not high enough, and we do see flutter echoes. We saw that when we laid out what the impulse response looks like. And we already analyzed this. The same formula holds for the reverb time. So if we now plug in the same kind of thing, now I've plugged in 2 seconds before. I used 1 second. So we need a delay of mt equal to 0.1 second. And so that gives us only 10 echoes per second. And it's not going to change. It's not going to keep growing. So that's it. And so very low echo density, and they're going to flutter. So not good. And again, just pointing out this conflict between conditions number 2 and number 4. We want those spikes on the group delay to be closely spaced, but we also want the echoes to be closely spaced. But the spacing for both of them is reciprocal to each other. So here we need a large M. I'm sorry, this is the echo density. We want the echo density to be large, and we want the peak spacing to be small. They both have reciprocal relationships, so we can't have that. We need a large M here. We need a small m there. So that's bad. So now what did Schroeder do? Okay, now he's starting to put things together. He asked the question, gee, how can we get a greater echo density? I like this all-pass characteristic because it gives me this nice flat frequency response, but I need more echoes. So Schroeder said, well, if I cascade a bunch of flat frequency responses, the result is a flat frequency response. So let's put n of these all-pass blocks in series, and we'll give each one the same gain value, but different m values. So that's the key right there, different m values. We'll see that in just a little bit. So let's look at it in the frequency domain. If we have a cascade, the frequency response of the cascade is just the product, and a magnitude of a product is the product of their magnitudes, and each of these goes to 1. So the product is 1. So a cascade of any number of all-pass filters, even different ones, are still all-pass. So luckily, we've maintained conditions number 1 and 6. Now let's look at, so that was in frequency domain. A cascade of systems has an overall impulse response that is a convolution of all their individual impulse responses. So take these two, convolve, take that result and convolve with the next one, all the way down to taking all of those convolving with the last one. So that's how we would think about that. And so here's the deal. If we choose all the M1s, right, we said they're different, or M sub i's, we said they're all different delay values. So each one of these blocks will have a different M value. So I've just denoted them as M1, M2, all the way out to M sub n. And Gardner and maybe Schroeder also use the term incommensurate. That's a little bit of a loose use of that term, but the bottom line is these integers should share no common factors. It doesn't mean that they're individually prime, although that would certainly work. It means that they're what's known as relatively prime. There's no common factors between them. So the claim is that increases the density of echoes. Now, one way that you can easily test this is to go into MATLAB and create an H1 that looks like this. It's a 1, 0, 0, 1, 0, 0, and just keep doing that for some number of repetitions. So that's a spacing of 3, right? 1, 2, 3. So that is an m equal to 3. Now let's make another one. Let's do H2 is equal to 1, 0, 0, 0, 0, 1, 0, 0, 0. These two things, this is spaced by 3, 1, 2, 3, 4, 5, spaced by 5. If you convolve those together, you'll see that the spacings that you get are a lot closer than either of them. And you'll get a very interesting mix. It won't be very regular. But if you made this one, if you put another 0 in here and another 0 here before we put another 1, now we've got 3 and 6. Those do share a common factor, and in fact, that common factor is 3 itself. If you convolve those two together using the conv command in MATLAB, you'll see that you always have a spacing of 3. So this incommensurate delays, or better, the delay integers share no common factors, will ensure that you get a more complicated echo structure from that convolution than you would from any one of the individual ones, or that you would get if these things were commensurate delays. That's the key. Now we can get dense echoes, and they will not be periodic. So we're on our way to satisfying conditions 4 and 5. So if we do pick these m sub i's to be incommensurate, or a more precise way to say it is they're relatively prime, they share no common factors, then the poles will also be distinct and more dense in frequency. So if we look at that, the angle of these poles, they're going to be spaced 2 pi over m1, and these are going to be spaced 2 pi over m2, and these are going to be spaced 2 pi over mn. So with all those integers being relatively prime, none of these spacings end up hitting each other. So you'll have no poles being kind of on top of each other. So you get lots of diversity in the spacing, and you can increase the density. Whereas if they had a common factor, you'd lose that increased density. You might increase it a little bit, but not as much. So this is working towards satisfying condition number 2, densely spaced modes. So again, think about the modes as being the poles, densely spaced poles around a circle. And so now, because we can choose these M1 through MN individually, we can keep each of those kind of, to a more reasonable value, but we can still get nice, closely spaced modes. So there's no longer this conflict, right? We can make the individual M's small to get echoes that are closely spaced, made even closer spaced because of the relative primeness. And we can then, even though each one of these has widely spaced poles, they're all interwoven to give a nice dense spacing around the circle. And they won't be periodically repeated because, again, relatively prime. So condition 3 is still met because all the poles are the same distance. So all these have the same G value. So everything is met. All 6 conditions are met. And so that's the beauty of this. Just by cascading a bunch of all-pass filters. So 2 stumbles, right? Did a comb filter, did a single all-pass, but all of that exploration led to the insight that led to something that looks like this. So this is right out of 1961 paper. I've modified it a little bit because I put in Z's. I don't think the paper has Z's in there. And these are the values that Schroeder suggested for these values or for these parameters. Schroeder programmed this or implemented this. There's some discussion in there about the challenges of running this on a very large mainframe IBM computer that probably filled a room and took hours and hours, if not days and days, to run. Today, we could implement this in MATLAB and run it in a matter of seconds, if even milliseconds, probably. And I did that, and this is what we got. And you can see, oh, look, the density keeps getting larger. This is the impulse response of this. So the density increases with time. And this looks remarkably like an actual real room's response. Now, does it sound perfect? No, it doesn't. But this is actually pretty good for 1961, the very first attempt at this that was successful. The light bulb that Edison first developed probably looked less like today's light bulbs than Schroeder's first impulse response looks like what today's reverb impulse responses look like. So, pretty good. Now, that was his 1961 paper. A year later, he's got a new paper out, and the first half of it, pretty much the first half of it, is he just goes back and rehashes everything he did in the first paper. Then he says, okay, those are the things I already looked at. Here's the new things. And he talks about 3 ways to improve. So he talks about mixing the reverberated and direct sound. So, he did that in the original all pass, but now he's doing it again, right? But that makes sense. That's how real reverb works. There is a direct path and there is a reverb path, all the reflected stuff. And he talked about putting a gap between that direct form and the reverberated sound. He's acknowledging that this is really just modeling the late reverb. So there should be a part in the middle or at the beginning where this stuff doesn't sound quite right. And then, 8 years later, he does finally publish a paper that talks about the early reflections. So he was probably already looking at that. Maybe he just got sidetracked on some other projects and finally got back to it. So those 2 are pretty straightforward. But then he says, let's think about making the reverb time to have some frequency dependence. Remember, we don't need a lot. But real rooms don't really have exactly the same reverb time at all frequencies. There's a little bit of frequency dependence. So he discussed ways to handle 1 and 2, and I alluded to that already. Just look back at our note set 5 in this unit, and we talked about, this modeling of early reflections, and we talked about adding a direct term and leaving a gap between the direct term and the late reverb where we can tuck in the early reflections. So we've got that. But let's talk about number 3 here, making the reverb time depending on frequency. So for that, he develops what he calls the comb filter approach. And you might say, wait, I thought the all-pass filter was the good thing. Well, it's really not just a comb filter. It's parallel comb filters together with a series cascade of all-pass filters. So that's what he had in his 1961 paper. And now he's going to take the comb filters that he had in the 61 paper, but he's going to put a bunch of them in parallel and run those into a cascade that he had in the 61 paper. So he calls it the comb filter approach, but really I think it should be called the comb and all pass filter approach. So the first thing he does is he kind of backpedals. He says, oops, I made this perfectly flat all pass reverberator. Do I really want to do that? If real rooms don't really have perfectly flat frequency responses. So he kind of backpedals a little bit and says, I'm going to try to make this a little less perfectly flat and try to get some of that irregularity in it. He talks about some experiments that people had been doing looking at the psychoacoustic characteristics of reverb. And here's a quote right out of this paper. Extreme response irregularities, we're talking about frequency response, are imperceptible when on the frequency axis, the density of these peaks and valleys, how fast it goes up and down along the frequency axis. If that density is high enough, you can't really hear those things. So he's going to allow that to happen now. And then he goes on and says, all right, so if I want a reverb time of 1 second, he analyzed that and says that means there's about 15 large response peaks in every 100 hertz interval. So he's kind of ignoring that going up by f squared thing there. But this is a reasonable value to kind of aim for. And he says, I can get that by just taking some comb filters, and he's going to play the incommensurate delay thing again to get those comb filters to have poles that will also interweave. So that gives a bunch of 15 response peaks in every 100 hertz interval. So that's how he settled on 3 or 4 parallel comb filters, all with poles interwoven to get that kind of density. And so he claims that that will give him satisfactory mode density. Now, it doesn't go up as f squared, so there is that, but it seems to work okay. But it doesn't give the echo density that you need. So we're right back to that making the density of the modes good enough doesn't give us the echo density that we want. So then he says, yeah, but I've got something that will create lots of echoes. It's that series cascade of all pass filters. So he's going to take the output of these, which will give the nice irregular spikes in frequency, and then run it through an all pass filter that will not perturb the spikes in frequency that he's getting from the comb filters, but it's going to make a lot of echoes. So kind of best of both worlds. And if he hadn't really played around with those early things and told us about them, maybe he wouldn't have come to this conclusion. So I'm a firm believer that when you're doing research, it helps to tell people about some of the off things that you might have done. Anyway, here's a picture. This is from Gardner's chapter 3, showing 4 parallel comb filters and only 2 all pass filters in series. But this was Schroeder's implementation in his paper. So right out of his 1962 paper, but I took the figure from Gardner's paper because it just shows it in a more modern setting. And then he gives some guidance on how to pick the gains and how to pick the delays. So remember, these M's have to be incommensurate, and these M's have to be incommensurate. And you probably ought to keep all of those incommensurate with each other just to be safe, although I'm not sure he states that. It gives you a guide for picking the M1 and the M4 with capital T. Remember, that's equal to 1 over Fs, so whatever our sampling rate is. You're going to pick the M1 to M4 so that those delays in seconds will be between 30 to 45 seconds. That's this 1 to 1.5 ratio. And then he says, now that you've got those, pick your individual gains according to this formula. where T sub R is your desired reverb time. So that's what he lays out for you. And then he literally just tells you exactly what to use for the other ones. So 5 milliseconds, 1.7 milliseconds. Seems odd that he would write those out in that order, but that's what he did. And then 0.7, our beloved 0.7 value for those G's. And unlike the Cascade all-pass filter one that I did in MATLAB and showed the impulse response, I didn't do that here. That's because in my actual course offering of this, that ended up being a homework problem. So I don't have that here, but you should be able to easily do that and see what it looks like and listen to it as well. And then this last gain G7 here just balances how much reverb you have relative to the direct path. So you can make it sound louder or softer. So that's it. That should sound not too bad. Not as good as modern day reverbs, because this was the very second, not the very first, but the very second attempt at this. But still, sounds remarkably good for something so simple. Okay, so then what? Well, that was 1962. Remember, 1970, Schroeder published a paper that said, oh, let's tuck these early echoes in here, and we'll get that with a sparse FIR filter. And he even talked about using the output of that early echo to drive the late reverb. So that gets even more echoes. So you can certainly do that. But then 9 years after that, a guy by the name of Moorer came out with this, and it's a really interesting paper. So you can see that the title is kind of intriguing, about this reverberation business. So it's not so much a academic paper as much as it is just saying, here are some of my musings and thoughts on doing this. And he made some improvements to this parallel comb series all pass form that Schroeder's did. So Schroeder had 4 parallel combs, Moorer went to 6, and Schroeder had 2 series all pass, and Moorer said, just do 1, and that should be enough. So in addition, he included a single low-pass filter in each comb filter's feedback. So this is one of the comb filters. This is not the full reverb, just one of the 6 parallel comb filters. And instead of just feeding this back and putting it through a G, he puts a filter H of Z in here, and there is that filter. It's a low-pass filter. And this idea actually was mentioned in Schroeder's 1962 paper. So Moorer is just fleshing it out a little bit more. Now, why did he do this low-pass filter? Well, that's a way to have the reverb time be different at different frequencies. So it actually decreases the reverb time at high frequencies. And remember, this is a plot for Boston Symphony Hall. If we were to draw a flat plane at the minus 60 dB level and see where that cuts through here, we would see that, I can't really see where this is going. Let's say it goes like that. It would cut through like here and then out here. So if we were to draw that on this time axis, we might see something like this. This is the time points at which this thing drops down by 60 dB. So high frequencies have a shorter reverb time, and this low pass filter will do that. So high frequencies will have a smaller number here than the low frequencies would. And so that's the idea. And there's more details in this paper. I'm pretty sure this paper is Googleable. Is that a word? Googleable? You can Google this. Just put this phrase in along with more probably. And you'll find a PDF of that, I'm pretty sure. Okay. What else happened? So that was 1979, 1992. Gardner is working on his MS thesis at MIT. If we think of Schroeder as the grandfather or godfather of all this, Gardner might be thought of as the prodigy child of Schroeder. Because really Gardner has made some tremendous contributions to this field. A lot of other people have as well, but his name just keeps popping up all over the place. And he wrote this chapter 3 that I based this note set on. So not only is he good at generating new ideas, he's very good at explaining them. But anyway, he was a master's student in 1992, and he was studying this stuff. He suggested replacing each of the all-pass filters in Schroeder's series cascade, whether it's just by itself or the series cascade following the parallel comb filters, either one. We're going to replace the all-pass filters by nested all-pass filters. So what is that? So here's a standard all-pass. So this would just be one stage in the cascade. Then we'd have another one of those, and another one, and another one. Schroeder said 4. Moorer said, Schroeder said 2. Moorer said, 4, I think? Moorer reduced it to 1, right? So what is Gardner saying? Well, however many you want to have, take this simple all-pass structure and take this z to the minus m. Remember, that by itself is an all-pass filter, right? What is the frequency response of a pure delay? Magnitude 1. Phase or group delay, m samples, okay? So take that and replace it with an all-pass filter, a more general all-pass filter. So take maybe this whole thing and put it inside here. It's sort of like those Russian nested dolls, right? And I guess you could go even farther. Once you put this inside here, then the thing that's inside there could have another doll nested inside and another doll nested inside that. So you could do this pretty crazily if you wanted to. But I think maybe Gardner just said, just nest it once. So then you can show that if this was all pass and you replace this by an all pass, then if A of Z is all pass, this whole structure is also all pass. That can be proved. And again, when I offer this course officially, that ends up as being a homework problem that I assign. Now we need to be sure that we don't get any delay-free loops. We talked about that a while back, Unit 1, I think, or maybe Unit 2. Yeah, Unit 2 when we talk about Chamberlain's filter. We talked about delay-free loops. We just want to make sure that as we go from here through here and back, that when we go around this loop, we have to go through at least one delay. A good way to ensure that is that whatever is here can always be factorable into a delay in series with an all-pass filter. So that's one way to ensure that. Just make sure that as you go around this loop, each time around you're going through some delays, and then you're good. So what does this do? Well, remember, this thing, which we're putting in here, that created a bunch of echoes because it's just, I cycled the wrong way. It's just cycling things around and around and around. So coming out are a bunch of recycled things, but all of those get recycled again. So it's kind of recycling all the recycled stuff. So doubly recycled. And that's definitely going to give us a lot more echo density, and it will increase the density with time, just like we see in real room. So more information on that in Gardner's MS thesis, and that also I'm pretty sure is available as a PDF somewhere online. You can just Google that if you want to read that. But then he went a little farther. He said, okay, that's the germ of the idea. That's the kernel of the idea. Let's see what we can do with that. He's going to put several of these nested all-pass filters in series. I'm not even sure if he hung some comb filters out in front. Maybe he didn't. I can't really remember. But then we're going to sum the taps between the blocks, not just take the output from the whole end as our output. We're going to go back inside in between each of those cascaded nested all-pass filters and tap that out and add them together. And, let's just put a low-pass feedback loop around it to get some frequency dependence. So this is right out of Gardner's chapter 3, but it's drawing on stuff from his thesis. Each one of these is one of these nested all-pass filters that we showed on the previous page. And here are all the intermediate taps, and we can set those to any values that we want. And here's the low-pass filter, and there's a lot more details in his thesis on that. But that's the basic idea. So that's going to create a very good reverb. So we're getting better as we go along. We're up to 1992. I threw in these last two slides here, not to go into great detail talking about them, but just to give you an idea how other people have kind of riffed on these ideas. So this is a paper. I don't know who this person is. Beltran. I think there were a couple co-authors. This was in 1999, and they're basically saying, hey, I looked at Gardner's ideas and I've applied them to model the reverb of a large room. And so this doesn't follow that simplistic view of just a bunch of nested all-pass filters, but there's a bunch of bells and whistles in here. So let's follow this all the way through here. So we've got an input that comes in, it goes through all these things, comes down here, goes through all these things, comes down here, and gets summed into the output. Now we also have a feedback through a low pass back into here. And then we have two other points that we've tapped off. So that's a la Gardner's intermediate taps, but not quite as systematic. And what are in all these stages that are all cascaded together? Let's see. Well, it's really just here and then here, because by then we're just getting hit by a gain. So an all pass, just a plain all pass with a particular delay and a gain. Another all pass with a particular gain and delay. And I'd be willing to bet if you checked 352 and 529, you'd find that they have no common factors. And then just some delays with a tap out in between. So it's not clear what those delays are doing, but probably just aligning things in some nice way. Now we come down, now we hit two nested all-pass filters with some delays in between. And I guess those are just allowing us to pick these things off at particular points in time so that maybe we can adjust the timing of those to sound better. So we've got cascade of two regular all-pass filters, cascade of two nested all-pass filters, and you can see, yes, this has an outer and an inner, and this has an outer and an inner one and an inner two. So yes, an actual nested doll. So outer, then a doll, and then another doll. So outer doll, inner doll, inner doll. Okay, so yes, so somebody did actually do that. And then a low pass filter with a specific cutoff frequency. So, you can find this paper. I gave you the link to it. You can read it. There might even be a link to some MATLAB, but you should be able to implement that with enough attention to detail to try to test that out and see what it sounds like. Okay, last slide. John DeToro, we mentioned him back in Unit 2 when we were talking about Chamberlain's filter. He wrote a series of 3 papers. It's a 3-part paper. In one of those, he talked about Chamberlain's filter. Then we also mentioned him when we talked about vibrato and flanger and chorus. So he talked about that in one of the parts of the paper. And he also talked about reverb. And he also talked about oscillators, I think primarily in the third part of the paper. We've not really talked about that. But in one of those, he did reverb. And this figure is not from his paper, but from Gardner's chapter 3 of that book that I pointed out. And again, I'm not going to go through all the details here, but De Toro claimed that this was a good simulation of a plate reverberator. So that's kind of interesting. Yes, we've seen that the units that you can buy have a knob that will allow you to set it to a large concert hall, a medium concert hall, a small room. But then we get into spring reverb, plate reverb, and then weird and wacky things. But yes, people don't want to put a big metal plate in their studio anymore. They just want a little box that when they want the sound of a plate reverb, because it makes you sound like you're recording back in the 1950s, and sometimes you want that. People like the sound of a plate reverb. So if you can get that from your digital reverberator, all the better. So this is what he laid out as an approach for that. And again, I'm not going to go through all the details. I don't think he actually has any nested all-pass filters here. These are all just regular, and you can check these numbers here. I bet they're all such that they don't have any common factors. You can see that there is some frequency-dependent decay in here. A couple other interesting things is here, in those two places, the delay is being varied with time. We saw that kind of thing in the vibrato. It's not clear whether you need to do interpolation here like we did, but I bet you do. Probably wouldn't sound right anyways, but it tells you that it's a 1 hertz sine wave sweeping 16 samples peak to peak. So just a little bit of shimmer on that, and maybe that's capturing the plate reverberator characteristics. As it bends, its distances change perhaps, and maybe that's why that's in there. Another interesting thing in here is this kind of cross-coupled structure that I think the quotes there are referring either to Gardner's term for this or De Toro's term, a reverb tank. So what's going on here, right? So we come through here, come through a bunch of all-pass filters. We come down here, and then we go into here and into here. And what happens? So the part that goes through here comes out and gets cross-coupled back into the other one. And the thing that comes out of here gets cross-coupled back into there. Interesting. So that's kind of bouncing sound back and forth between these two individual substructures. Okay. And then the final interesting thing here, well, there's also some frequency-dependent decay that is put in there. Same filter, presumably, an H2 of Z. So that gives some frequency-dependent reverb time for that. But what's the A, B, C, D, E, and F? I added some red circles there to call those out. The outputs, both left and right, so this was a stereo implementation, are just tapped off from these positions. So A in two different time positions. So I'm getting a little loose with the notation here because I needed to squeeze it into this time here. But these are just relative delays at those positions. So it would really be like n minus 266 or something like that. There's more detail probably in Gardner's paper and certainly in De Toro's paper. But basically we're tapping off at 6 different places with different time references and adding and subtracting those things. How did John De Toro come up with this? No idea. So my guess is this probably is a pretty reasonable plate reverberator. So that's it. We're done with this set of notes. we'll move on to a more modern view of Reverb, but still couched in the starting point of Schroeder, but just a extension of those ideas. And we'll see that in the next note set, and I hope that I'll see you there.